Hi everyone, and welcome back to my channel. Today we are going to talk about solving math applications involving exponential models. Exponential models are commonly used in a variety of fields, including finance, science, and engineering. So knowing how to solve these problems can be incredibly useful and can help you better understand how exponential growth or decay works. In this video, we'll go through some examples of real-world problems that can be solved using exponential models, and I'll show you step by step how to approach these problems. So let's dive in right now. Let's look at the following situation. An average new car depreciates 15% in value each year. How long does it take for a new $40,000 car to depreciate down to $10,000 in value? Before I start working with these large numbers, I want to show a particular property that is quite relevant here. It's going to make things easier in my opinion. And I'm going to do it only with variables, just to start with that. So for example, let's say that when t is equal to 0, the value of this object is equal to a. A can be anything. Then what will be the value a year later when t is equal to 1? In order to calculate the value a year later, we're going to go a, the value when it was new a year ago, minus the rate of depreciation times a. So minus 0.15 a. And if you notice now, these two terms are like terms, so I can subtract them. 1 minus 0.15 times a. That's going to be 0.85a. So then, now using function notation, that means that if v of 0 is equal to a, then v of 1 is going to be equal to 0.85 times v of 0, the value of the object a year ago. And notice how it is a factor of 0.85. 85% is the worth of the object a year later. And if I actually rearrange this expression here, this is like saying that the ratio between the value at 1 over the value at 0 is equal to 0.85. And I'm hoping that you remember that when we're dealing with an exponential function, the ratio of the y values between consecutive x values, when the x values are only one step away from each other, when you consider the ratio of those y values, that ratio is equal to b. We were calling that the common ratio. Again, if you consider the ratio of the y values at the x values being a step away from each other, like in this case, v of 1 divided by v of 0. 1 and 0 are a step away from each other. That ratio is always equal to the common ratio. In this case, this is equal to b. So this is telling us that b, the base of our exponential model, is equal to 0.85. Okay, so because we're dealing with exponential models, this is tremendously helpful because now we actually have the base of the exponential model that will represent this situation here. Now, if you forgot about the common ratio, I will make sure to link that relevant video in the description box below so that you can go ahead and watch it a bit later. So then again, now continuing. This situation is an exponential model. We're going to use the model v of t equals a times b to the t. And I'm using v for value. Now we have to go ahead and find A and B so that we have a complete model. Now I already have B, so I can improve my model. I can say that V of t is equal to A times 0.85 to the t. So that's what I have. And if I want to find A, then I'm going to set t equals 0, because I know the value of the object at 0, and that is going to give me A times 0.85 to the 0, which is going to be equal to A. Very nicely. All right, but then I already know that V of 0 is equal to 40,000, right? 40,000. So then this is telling me that A is equal to 40,000. And please know that this is something that is obvious. It's obvious that if you plug in 0 for t, b to the 0 is going to be equal to 1. So you're always left with A. And A is the value at 0. So you can just immediately go ahead and set A equal to 40,000. So then now I have that the value V of t is going to be equal to 40,000 times 0.85 to the t. And this is the model that is describing this particular situation. Now that I have the model, I can go ahead and try to find the actual answer to the question. And the question was, how long does it take for a new car to depreciate down to $10,000? How long? So if we set the value equal to $10,000, what will be the value for t? So if V of t is equal to $10,000, then the question is, what is t? We're solving for t. So we're going to do just that. We're going to take the function and set it equal to $10,000, and we'll try to find t. So that means 40,000 times 0.85 to the t equals to 10,000. And now, folks, we want to be able to isolate t. We want to be able to solve for t. In order to do that, I'm going to have to divide both sides by 40,000. Just like this. On the left side, the 40,000s will cancel. On the right side, I can simplify the fraction. And now I am going to have 0.85 to the t equals to 1/4. And what I need to do now is to find a way to bring t down so that I can actually isolate it, so that I can find the value of t. And the only way to do that in this particular case, or the easiest way, is to take the log of both sides. So we're going to have the log of 0.85t equals to the log of 1/4. And now by using properties of logs, we can take the exponent down in front of the log. This is the power rule for logs. That means that we're going to have t times log of 0.85 equals to the log of 1/4. Final step will be to divide both sides by the log of 0.85. Same thing over here. Then the logs will cancel, and now we're going to have t completely isolated. We're going to have that t is equal to the log of 1/4 divided by the log of 0.85. Now at this point, that's when you grab your calculators and you approximate this to get a better sense of how long it will take. And when you approximate this, you're going to get approximately 8.53 years. Well, that means that it will take around 8.5 years for the value of the car to depreciate all the way to $10,000. Always remember at the end of every application, on assessments for example, to end with a final written conclusion.